So let's take a look at this situation. There's a rectangular box with a base that's 10 feet by 15 feet. So this is going to be the front face of the box. And let's say that this is the 10 feet. And then it's going to go back like this, where this is going to go back by 15 feet. And I asked to find the hydrostatic force exerted on one end of the box. So I could have done the front end or I could have done the side. So I'm going to do the front. So I'm going to be using the 10. In that situation, we actually aren't going to use the 15. If it said to find the total amount on all of the ends, then we would need to find the force on this end, then do the same integration with a 15 instead of a 10, and then find all the sides of the box. But it just says one end, so we'll do this end right here. Okay, so to begin with, the amount of force created by water is 62.5 pounds per cubic foot. So that's basically saying if you were to take a 1 foot by 1 foot square, find the area, then of course the area is 1 foot squared. And if you multiplied that by this rate, you would get, so multiply this by 1 square foot, and then square feet will cancel 2 out of the 3, and then it would leave 62.5 pounds per foot. So this is not quite a force, because a force would have to just say pounds. So this is actually a rate. So this is saying there's going to be 62.5 pounds for every foot you go underwater. So if you were to, for example, take that little rectangle, or excuse me, square, and then you move it 2 feet underwater, then you could multiply by the 2 feet, and then you would have feet cancels feet, and the total would be in pounds. So then that would be the amount of force. Okay, so now let's take this basic idea and transfer it over to here. So for one thing, I need a coordinate system. So I'm going to say that this is the x-axis and this is the y-axis. And instead of using a square right here, I'm going to use a rectangle and say, well, what if you had a rectangle that is underwater right here? And then how much force is on that? So this rectangle, it could be at the bottom, it could be in the middle, it could be at the top, doesn't really matter where you draw it, but because it's going to have to move up and down along the y-axis, then this is going to be called delta y. Usually we use delta x, but that's for going left to right. For going up and down, I need to use y. Okay, so the area of this rectangle, which is the first thing that I did over here, find the area of the square. It was 1 times 1, so it's 1 square foot. So for this, it is delta y is the height, and then the length is 10 feet. So doing this part over here is going to be delta y times 10. And then the next thing I did is I multiplied that with the 62.5. So then multiplied that with a 62.5. And so that would basically get us to this part when I multiplied by the 1 square feet. So this is feet times feet. So I'm multiplying by square feet. So we're basically down to this part right now. The next thing I needed to do is see how far underwater it is. Well, if water's been filled to a 4-foot level, that means that up here on the y-axis, it's going to 4. So that means that this rectangle could start at the bottom where y equals 0, and eventually it would go up and up and up until it gets to a 4. So we could say, well, this right here, I don't know what number it is. It's some number between 0 and 4. So I would just say that it's y. Now y means you're going from the bottom up to y. But then we're saying that this thing has been submerged underwater. So how far underwater it went would actually be the other side. So its depth would be 4 minus y. And then that would be just like this part when I said if you submerge it 2 feet underwater, you would then multiply, the feet and feet would cancel, and you would get the pounds. So we also need to multiply by how far underwater it is, which is the 4 minus y. So then we would get to this point where the feet and feet cancel, and then this is in pounds. So now we need to have this rectangle go from the bottom and add up all of the force as it moves all the way to the top. And that is what the integral does. So integrate from 0 to 4. So by the way, sometimes you might set these up backwards, or you might, for example, put y here, and you'll get the same number, but it'll be negative because you're going the opposite direction. So hopefully we're going to get a positive number here. Okay, so the 10 times 62.5 is going to be a 625. I'm going to go ahead and factor out the 625. And then we need to integrate from 0 to 4. The 10's been factored out. This is the actual function, 4 minus y. And then in integration, the delta y becomes dy. And after all the challenging integrals we've been doing recently, this one is pretty easy after we finally have it set up. So the antiderivative of 4 will just be 4y. And the antiderivative of y is going to be y squared over 2. And then evaluate from 0 to 4. Technically, I'm supposed to put a straight line right there, but good enough with the bracket. So let's see, that's going to be a 625, and then substitute 4. So we've got 4 times 4 minus 4 squared over 2. And then minus, when you substitute 0, that's going to be 0, and that's going to be 0. So minus 0, that makes it simple. Then 625, and can I even do this without a calculator? That's going to be 16. This is going to be 16 divided by 2. So it's a 625 and then times 8. Okay, that's enough showing off without the calculator. Then with the calculator, 625 times 8 is a nice even, sorry if you can't see it, but it says 5,000. So that would be 5,000 total pounds of force on the side of the swimming pool or rectangular box.